I'll be presenting about a well-known example of a continuous nowhere differentiable function, the Weierstrass function. It is defined as this infinite series of cosines, with a leading geometric coefficient labeled as a, an odd integer power in the argument labeled as b, and the product of a and b being sufficiently large. Over the course of the presentation, I will demonstrate the series convergence, continuity, and then give a brief outline of the nowhere differentiability proof. Let us prove that the series defining the function converges uniformly. We may begin by defining the partial sum of the series. Subtracting these partial sums from the limit function, we get an infinite series starting at a later term. We can then show, by comparing to a geometric series, that this difference is of an arbitrarily small size. Since this argument applies for all values of x, the convergence is uniform. Using the uniform convergence, we may move on to show the continuity of the total series. By the definition of convergence, the differences between the function and the partial sums must be arbitrarily small. Since each partial sum is a finite sum of cosines, we know that the partial sums themselves must be continuous. Mathematically, that means that the values between outputs of the functions can be arbitrarily small, provided our inputs are arbitrarily close. Combining the outcomes of the two definitions and the triangle inequality, we demonstrate continuity of the function. Proving nowhere differentiability is quite tedious, taking up 2 full pages of calculations in a precise proof. Visually, one may infer this by noticing how, at every point, the function seems to look like a steep absolute value, which wouldn't be differentiable at the vertex. The proof involves the following 3 steps. Identify the left and right limit of the derivative at an arbitrary point. Evaluating them cleverly, we would reach the same result, but with opposite signs. Since the left and right limits are of opposite signs and non-zero, the derivative does not exist. In conclusion, the Weierstrass function is an interesting demonstration of the potentially counterintuitive notion that continuity does not imply piecewise differentiability. If you are interested in reading the proofs in more detail, there are plenty of resources online to see the full descriptions, such as the one I used. Thank you.